Howdy, today on Flipping Science we're looking at reaction rates. So the science understanding we're going to look at, rates of reaction at different times can be compared by considering the slope of a graph of quantity or concentration of reactant or product against time, and you need to draw and interpret graphs representing changes in quantities of concentration of reactants and products against time. So let's talk about reaction rates. Chemical reactions take place at a variety of speeds. Some reactions are really quick. So precipitation reaction, they're usually really fast. They happen normally under a second. Organic preparations like ester making, they can take place over minutes to hours. Rusting of iron is an example of a very slow reaction. So there's many different reaction rates out there. It's very important in industry to know how quickly a reaction occurs and how to change the speed of a reaction. And let's have a look why. So in the 1980s there was a disaster in a town called Bhopal in India. What happened was there was an underground tank of methyl isocyanate, which is used to make pesticide. When you put it in water, it produces an exothermic reaction, so it gives off a lot of energy, and it turns from liquid into gas, and that gas is quite toxic. In the plant at the time of the disaster, their safety systems weren't working, so what should have been a reaction that could have been contained and slowed down instead accelerated, and it led to a release of this toxic gas. The toxic gas flowed through the air down onto the town and killed an awful lot of people. So if they had been able to slow down the reaction rate of the methyl isocyanate turning into the gas, then the disaster wouldn't have happened. So what is the rate? So rate of reaction is a measure of how fast or slow a reaction occurs. It's a measure of the change that occurs in a reaction in a unit of time, so per second, per minute, per hour. Chemical equations that we write down, they don't tell you how fast or slow a reaction is. That's found by doing experiments. Generally speaking, if we're going to measure the rate of reaction, we need to look at the amount of reactant that's used up per unit time, or the amount of product produced per unit time. So let's look at an example. So down here we have a chemical reaction where we're placing magnesium in an acid, hydrochloric acid I think. We can see initially we're getting a whole heap of bubbles and it's reacting quite quickly, but over time the bubbling is reducing, so there's fewer and fewer bubbles being produced until the reaction stops, and we don't see any more further reaction happening. So we can see there's a change in reaction rate. Initially the reaction rate is quite high because we're getting lots of bubbling and fizzing occurring. Then over time that bubbling and fizzing reduces, so the reaction rate is dropping, and then finally the reaction stops. So here's an ionic equation for that reaction. So what's happening is the solid magnesium is reacting with the hydrogen ions from the acid, producing magnesium ions and hydrogen gas. We could measure the rate of the reaction in many ways in this reaction. We could look at how much magnesium is being used up per unit of time, how many hydrogen ions are being used up, the amount of magnesium ions being produced, or the amount of hydrogen gas being produced. All of those are ways that we could determine the rate of the reaction. So here are two ways that we can measure that rate. In this example here we have the acid in a beaker on a balance, and we place the magnesium in, we put a little watch glass over the top so that we can stop the liquid from splashing out. But as the reaction occurs, we should be able to see a drop in mass. As the hydrogen gas is produced, flows out, that will make the remaining system have less mass. So we should see the mass dropping. Over here, another way of doing it is collecting the amount of hydrogen gas being produced. So as the reaction is occurring, we have a funnel over the top of the magnesium. We collect the bubbles go into a burette, and then we could measure the volume of the gas being produced. So that's a couple of ways we could measure the rate of reaction. So here's an example set of results. So in this example, we're measuring the volume of hydrogen being produced, and that should be a superscript cube. This program doesn't do that. Now the data doesn't really tell us much when we just look at it in terms of numbers, but we can see that there is an end point here when the volume of hydrogen isn't changing, and if we look at our numbers as time goes on, we should see that the amount of volume being produced per minute is reducing. Now I'll go through how to make graphs in class, and I'll make another video on how to make graphs too. Let's have a look at the results in a graph form. So here is the results in graphical form. And we need to be able to interpret these graphs to determine what the rate is doing. Now, if we have a time graph, the rate of a reaction is the slope of a graph at any point. And we'll go through how to measure that shortly. But if we have a look at the graph, we can see initially we have quite a steep gradient, a steep slope, and that tells us that the rate of reaction is quite high. The amount of hydrogen gas we're producing per minute is quite high initially. As the reaction goes on, however, the slope of the graph starts to flatten out. So that means we're producing less hydrogen gas per minute. And then finally we get to the point where the rate of reaction stops. We're not producing any further hydrogen gas. So when the slope is really, really vertical, that tells us we've got a high rate, and when it's horizontal we've got a low rate, and then as it changes in between we get a difference in rate. So to understand why this is, we need to talk about what a chemical reaction is, and this is based on an idea called collision theory. So in collision theory, your reactants have to hit each other, have a collision, successfully in order to produce a product. What that means is when the reactants, so in this case we've got hydrochloric acid and iron, when the reactants hit each other, they need to hit each other in the correct orientation so that bonds are broken, but also with the right amount of energy to break the bonds. So in this case we're breaking the bond between the hydrogen and the chlorine atom, and then we're going to be forming some bonds between hydrogen atoms later on, and also producing iron ions and chloride ions. So for this reaction to happen, we have to have the hydrochloric acid hitting the iron atom at the right amount of speed, so it has the right amount of energy, and in the right orientation so that those bonds are broken. The more frequently this happens, the faster the reaction rate. So the more collisions you get, and what we call more successful collisions you get, so the more collisions that break those bonds, per unit time, so the more successful collisions per unit time, the faster the reaction rate. So initially in our magnesium and hydrochloric acid system, we've got a whole heap of magnesium and a whole heap of hydrochloric acid, so there's plenty of atoms to bump into each other that will produce the products. Over time, however, the magnesium starts to be dissolved by the hydrogen ions in the acid, and that reduces the amount of magnesium present. So there's not going to be as many collisions between the magnesium and hydrogen ions, until eventually you either run out of magnesium metal, which is what we saw in the video before, or you run out of hydrogen ions. When that happens, you don't get any further reaction. So let's have a look at an example question. Let's have a look at the question. So here we have a graph. We've got a volume of gas being produced over a period of time. So very similar to what we've had previously. The question is, when did the reaction stop? So we want to have a look along the graph until we see that it makes a horizontal point. In that case, it's around about here. So that lines up with 90 seconds. So the reaction stopped at 90 seconds. Question 2 says, what is the reaction rate at 40 seconds? 40 seconds is here. We need to figure out the slope of the line at this point to give us the reaction rate. That's one way of measuring reaction rate. So we need to draw a slope of the line, so a tangent that's kind of touching the point at 40. That's not too bad. That's not too bad. Okay, so now we need to calculate the slope of that line to figure out what the reaction rate is at that time. Okay, so to find the slope, it's a y step over x step. So y2 minus y1 over x2 minus x1. Okay, so we need to look at our y and x values for the points we're going to use. I'm going to use this point here, and I'm going to use, let's use that point there. Okay, so let's write down what our coordinates are, and then we can figure out from there. So our, it goes x, y, doesn't it, when we do maths? So x first, so we are at here 52, 54 seconds. So 54. And then our y value is 60. Okay. So that would be x2, y2. Okay, and x1, y1. That's fine. Let's go to this point here. So our x value is 28 seconds. So 28. And our y value is 46 seconds. 46. Okay, so there's our coordinates. So let's do y2 minus y1. So that's going to be 60 minus 46 over 54. That's our x2, 54, minus 28. So let's do this in our calculator. Now 60 minus 46 is going to be 14. So 60 minus 46. 14, good. So we've got over here 14. It's going to be divided by, so 54 minus 28 is 26. 26, so 14 over 26. So go to our calculator, 14 divided by 26, 7 on 13, which is 0.54. Now we've used two significant figures for this, so we'll go 0.54. write the equals down here. So 0.54. Now, what's our unit here? It's going to be volume of gas, so cubic centimeters per second. Centimeters cubed per second. Okay, so that's our unit there. Explain why the rate of reaction would be greater at 10 seconds. So at 10 seconds over here, so 10 seconds is here, if we look at the slope of the line here, and I'll just draw it, we can see that that's a little bit more vertical than that one there is. So that means the rate of reaction is higher. So why is it? So initially there's going to be more collisions between reactant particles, and therefore more successful collisions between reactant particles, as there are more reactants to collide with each other to produce a product. As time goes on, there's going to be fewer reactants present to collide with each other, so therefore the amount of successful collisions is going to be lower, and therefore the rate of reaction is going to be lower. So less product will be produced in the same amount of time. So today in Flippin Science we looked at rate of reaction and graphing rates of reaction. That's it for Flippin Science today. See ya.